Hello everyone, I am Dipanji from Basic Chemistry Honors 3rd year. Presentation on photochemistry. Photochemistry is defined as that branch of chemistry which deals with the study of interaction of radiation with matter, resulting into a physical change or into a chemical reaction called photochemical reaction, whose rates and mechanism are studied after initiation by radiant energy. Though the term radiation includes all type of electromagnetic waves from very low frequency microwaves to medium frequency infrared, visible and ultraviolet radiations to high frequency X rays and gamma rays, the radiation of photochemical importance are those which lie in the visible and ultraviolet region from 8000 to 2000 angstrom. Thus, the two main processes studied under photochemistry are photophysical processes, photochemical processes, or photochemical reactions. Photophysical processes are those processes which take place in the presence of light but do not result into any chemical reaction. These processes arise on account of the absorption of light by the substances followed by the emission of absorbed light. If the absorption of light is emitted instantaneously, the process is called fluorescence. If the absorbed light is emitted from after some time lag, this process is called phosphorescence. Further, if the energy of the light absorbed is sufficiently high, the electrons may not only jump to the outer levels but may leave the atoms completely. The process is called photoelectric effect. Thus, photophysical processes include phenomena like fluorescence, phosphorescence, and photoelectric effect. Photochemical reactions are those reactions which take place by absorption of light by reacting substance. These reactions are generally brought about by the absorption of light radiation of visible and ultraviolet region which lie between 8000 to 2000 angstrom as already mentioned above. In these cases, the light energy absorbed is stored within the substance and then used for bringing suitable light. Examples: synthesis, decomposition, oxidation, reduction, polymerization, isomeric change, etc. Two well-known examples of photochemical reactions are combination of hydrogen and chlorine to form hydrogen chloride. H2 plus Cl2 gives 2HCl. Photosynthesis of carbohydrate in plants taking place in the presence of chlorophyll, the green coloring matter present in the leaves. 6CO2 plus 6H2O, light, chlorophyll, C6H12O6 plus 6O2. It may be pointed out that the photochemical reaction that take place when incident photon has sufficient energy so that it can result in the excitation of the reactants from ground electronic state to excited electronic state Br2 in a mixture of H2 and Br2, as will be discussed later in the chapter. Difference between photochemical reaction and thermochemical reactions, or simply called thermal reaction. The main points of difference: a thermochemical reaction and a photochemical reaction are summed up in the table below. Difference between photochemical reaction and thermochemical reaction. These reactions involve absorption of heat. These reactions involve absorption of light. They can take place even in the dark. The presence of light is the primary requisite for the reaction to take place. Temperature has significant effect on the rate of a thermochemical reaction. Temperature has very little effect on the rate of photochemical reaction. Instead, the intensity of light has a marked effect on the rate of photochemical reaction. The free change energy delta G of a thermochemical reaction is very negative. The free change energy of a photochemical reaction may not be negative. A few examples of photochemical reaction for which delta G is positive and still they are spontaneous are synthesis of carbohydrates in plants, ozonization of oxygen, decomposition of HCl and H2 and Cl2. In these reactions, the activation energy arises from the intermolecular collisions or it is supplied in the form of heat. In these reactions, activation energy is acquired by the absorption of photons of suitable energy. When a reaction mixture is exposed to heat radiation, all the reactant molecules absorb these radiation and get excited almost to the same extent. When a reaction mixture is exposed to radiation, the molecules one of the reactant may get excited independent of the presence of other species. In the present chapter, we shall discuss mainly the laws of photochemistry, examples of some photochemical reactions, the mechanism by which they proceed, and certain terms like fluorescence, phosphorescence, chemiluminescence. Laws governing absorption of light. When a monochromatic light consisting of a single wavelength, is passed through a medium, some light is absorbed by the medium and hence the intensity of incident light decreases. The decrease of intensity on passing through a pure homogeneous medium, pure liquid, is governed by Lambert's law, and the decrease of intensity on passing through a solution is governed by Beer's law. Lambert's law. This law is put forward by Lambert in 1760, states as under: when a monochromatic light is passed through a pure homogeneous medium, the decrease in the intensity of light with thickness of the absorbing medium at any point x is proportional to the intensity of the incident light. The intensity of the light at point x just before entering into the thickness mathematically minus di by dx is directly proportional to I, or minus di by dx is equal to ki, where di is the small decrease in the intensity of the light on passing through a small thickness dx. I is the intensity of incident light just before the entering the thickness dx, in the constant of proportionality. K is called absorption coefficient depending upon the nature of absorbing medium. The intensity I at any point x from the start of the medium can be found in terms of the original intensity I naught as follows. Equation 1 can be written as di by I is equal to minus k dx. When x is equal to 0, I is equal to I naught, x is equal to x, I is equal to I. Integrating equation 2 between limits x is equal to 0 and x and I is equal to I naught to I, we get di by I naught to I is equal to minus k dx, x0 to x is equal to x, or I ln I by I naught minus kx, I is equal to I naught e raised to power minus kx. This equation expresses how the original intensity I naught is reduced to intensity I after passing through a thickness x of the medium. The difference between I naught and I obviously gives the intensity of light absorbed. Thus, I naught minus I is equal to I naught minus I naught e minus kx. Equation 4 can be expressed in another form, which can be derived as follows. Equation 3 can be written as 2.303 log I by I naught is equal to minus kx. Log I by I naught is equal to minus k by 2.303x. Log I by I naught is equal to minus kx, or I by I naught 10 raised to the minus kx. I is equal to I naught into 10 raised to the minus kx, where k dash is equal to k by 2.303 is called extinction coefficient of the substance. Now, it is a quantity which is called absorption coefficient or absorptivity of the substance. The physical significance of the extinction coefficient or absorptivity follows more clearly from equation 6, which can be rewritten as k is equal to minus 1 by x log I by I naught, 1 by x log I naught by I. Log I naught by I is equal to 1, k dash is equal to 1 by x. Log I naught by I is equal to 1 means I naught by I is equal to 10. I is equal to 1 by 10 I naught. Hence, extinction coefficient or absorptivity may be defined as follows. The extinction coefficient or absorptivity is the reciprocal of that layer thickness expressed in centimeter at which the intensity of light falls to 1/10 of its original value. Beer's law. This is an extension of Lambert's law put forward by Beer in 1852. It is applicable to solutions and state as under: when a monochromatic light is passed through a solution, the decrease in the intensity of light in which the thickness of the solution is directly proportional not only to the intensity of the incident light, also to the concentration of the solution. Thus, for a solution, mathematically we have di by dx directly proportional to I multiply C minus di by dx is equal to EIC is pronounced as epsilon, where epsilon is a constant proportionality and is called molar absorption coefficient. Its value depends upon the nature of the absorbing solute and wavelength of the light used. Equation 8 can be written as di by I is equal to minus epsilon dx. At before integrating the equation between the limits 0 and I is equal to I naught, we get di by I is equal to x0 to xx minus dx ec, or ln I by I naught is equal to minus ecx. I by I naught is equal to E minus epsilon Cx. This equation shows that the intensity of monochromatic light decreases exponentially from I naught to I with the increase in thickness x and concentration c. The intensity of light absorbed by solution when it passes through a length of x of the solution will be given by IAB as I naught minus I naught minus I naught ECX, I naught 1 minus ECX. As before, the equation 9 can be expressed in the another form. For this purpose, we can rewrite this equation as 2.303 log I by I naught minus epsilon Cx, or log I by I naught epsilon by 2.303 Cx. Log I by I naught is equal to epsilon Cx, I by I naught 10 raised to the power minus epsilon dash Cx, or I is equal to I naught 10 epsilon dash Cx, where epsilon dash is equal to epsilon by 2.303, was earlier called molar extinction coefficient. Now it is this quantity called molar absorption coefficient or molar absorptivity. The physical significance of the molar extinction coefficient or molar absorptivity follows from epsilon dash is equal to 1 minus 1 by Cx log I by I naught, I by Cx log I naught by I, where C is equal to 1 m log I naught by I is equal to 1, then epsilon dash is equal to 1 by x log I naught by I is equal to 1 means I naught by I is equal to 10, I is equal to 1 by 10 I naught. Hence molar extinction coefficient or molar absorptivity may be defined as the reciprocal of dead thickness of the solution layer of 1 molar concentration, which reduces the intensity of the light passing through it to 1/10 of its original value. It may be pointed out that gases follow Beer's law and not Lambert's law. Unit of molar absorptivity or molar absorption coefficient epsilon dash is equal to minus 1 by Cx log I by I naught, where log I by I naught is a dimensionless quantity. In SI units, X is meter, C is in mole meter per cube. Hence, we have epsilon dash meter cube per mole per meter square per mole. However, usually concentration are expressed in mole per liter molarity, length X in meter, and the units of epsilon dash then be epsilon dash L mole per centimeter, m minus 1 per centimeter. Some other terms commonly used in spectrophotometry. Spectrophotometry deals with the measurement of intensity of the light absorbed when it is passed through a sample of known thickness and concentration. Measuring the intensity of transmitted light relative to the depth of incident light, it is especially useful when one substance in the reaction mixture has a strong absorption in the spectral range. In these studies, the following terms are commonly used. Transmittance. The ratio I by I naught is the ratio of intensity of the transmitted light from the solution to the intensity of incident light. I naught is the fraction of incident light transmitted, is called transmittance. Transmittance is equal to I by I naught. Absorbance or optical density or extinction. The logarithm of reciprocal of transmittance log 1 by t or log I naught by I is the called absorption A or extinction E, formerly called optical density D. Absorption is equal to extinction is equal to optical density log 1 by t I naught by I. Specific extinction coefficient. It is defined as the extinction or optical density or absorptions per unit length and unit concentration of the solution. Ks is equal to d by Cx, molar extinction coefficient. Substituting the value of from equation 16 and 13, we get minus log I by I naught minus log t is equal to A or d epsilon dash Cx. Thus, if x is equal to 1 centimeter and c is equal to 1 mole per liter, epsilon dash d or A, hence molar extinction coefficient may be defined as optical density or absorbance of the solution having 1 centimeter thickness and concentration equal to 1 mole per liter, minus log I by I naught minus log t A or d epsilon dash Cx. Thus, a plot of absorbance of versus concentration C will be a straight line passing through the region with slope epsilon dash x as shown in figure 4.2. The dotted portion of the curve shows deviation from linearity at high concentration. Limitations of Beer's law. The law holds good only for monochromatic radiation. This law is applicable only to dilute solution. At higher concentration, the interionic interactions disturb the absorption of incident light radiation. The temperature should almost remain constant. Too much rise in the temperature shift the absorption band towards longer wavelength called bathochromic shift. Laws governing photochemical reactions. Laws of photochemistry. There are two important laws of photochemistry Grotthus Draper law. This law is called first law of photochemistry. It was put forward by Grotthus on theoretical grounds in 1818 and confirmed by Draper on experiment in 1839. It states as under: when light falls on a body, a part of it is reflected, a part of it is transmitted, and rest of it is absorbed. It is only the absorbed light which is effective in bringing about a chemical reaction. The above law, however, does not imply that the absorbed light must have resulted into a chemical reaction. The absorbed light may simply bring about phenomena such as fluorescence, phosphor, etc., as mentioned in the section 4.1. In case of potassium permanganate solution, the light energy is absorbed strongly, but no chemical effect is produced. Further, is in some cases it is observed that light energy may not be absorbed by reacting substance directly, but may be absorbed by some other substance present along with reacting substance. The energy thus absorbed is then passed on to the reacting substance, and this process is called photosensitization and has been discussed in detail in section 4.11. A well-known example is that a photosynthesis of carbohydrates in plant where chlorophyll acts as photosynthesizer. The expression for the light absorbed when it passes through a pure liquid and through a solution have already been derived in section 4.3. Stark-Einstein's law of photochemical equivalence. This law is called second law of photochemistry. It was put forward by Einstein and Stark. Every atom or molecule that take part in a photochemical reaction absorb one quantum of the radiation to which the substance is exposed. If mu is the frequency of the absorbed radiation, then the energy radiation and each reacting molecule is one quantum. The energy absorbed by one mole of the reacting molecule will be given by E is equal to NH nu, where N is the Avogadro number. Putting mu is equal to C by lambda, we will write E is equal to NH C by lambda, where C is the velocity of light and lambda is the wavelength of absorbed radiation. The energy possessed by one mole of photons or the energy possessed by one mole of reacting molecules is called 1 Einstein. Thank you.